If your vision calls for increasing the scale or scope of Scala-based technology, Micronautics Research, the Scala Enablement Company, can help your organization succeed with Scala projects on time and on budget. Micronautics Research offers mentoring, training, software development, and cutting-edge publications.
A little while ago, I wrote this guide called Effective Scala. And the goal of this website, or essay, a collection of essays really, was more or less to codify the kinds of best practices that we'd have sort of encountered at Twitter while constructing our very large systems there. It actually gained quite a lot of traction and has been edited and added on to over time. And I think is still today a pretty good and comprehensive guide of what we consider at Twitter sort of effective use of the language. However, it doesn't go too much into motivation for a lot of things. It's pretty sort of short and concise and tries to sort of stay factual. And so I'm hoping today to sort of highlight some of the snippets and sort of motivate them better and talk about them. And as I was thinking about this, how to sort of go about demonstrating this, I figured actually an example would be really nice. Because as it turns out, your sort of most recent thing that you worked on usually reflects what you think are the best practices as of today. And those best practices tend to change over time. And so what I decided to do actually was to take what I literally worked on last week and show you guys how awesomely I employed a set of best practices and what great results came from it. And then hopefully I will convince you that these are good ideas. And actually, most of what I'm going to talk about actually sort of falls outside of things that are in effective Scala, and I'm actually going to go back and sort of add them in. And so you'll get a preview of, I don't know, the next Git commit on effective Scala or something. So what I'm going to talk to, what I worked on last week was something called finagle mux. Finagle is our sort of network and RPC stack at Twitter. And one thing that we've sort of been lacking is sort of a true multiplexing session protocol. And so far, we've more or less been using a vanilla thrift protocol. I don't know if you're familiar with thrift. But thrift is lacking in many regards. And in particular, it doesn't come with built-in multiplexing. And there are a lot of other things that we want to do that sort of beyond just multiplexing that requires a properly thought-out session layer and so on and so forth. And so we endeavored to build our own. Of course, after going through and making sure that there wasn't something that really fit our needs, because we don't want to invent when we don't have to. And the basic criteria for this network protocol was that, first of all, it has to have sort of a separate and distinguished set of control frames. And so I should be able to talk out of band between my client and server, independently of the messages that I pass. I should be able to multiplex messages simply, which means basically I need to have several outstanding messages on a connection at a time. My concurrency shouldn't be tied to the number of connections that I have open. And it needs to be future-proof, and so it needs to sort of accommodate for a lot of the kinds of things that we anticipate needing in the near or far future. And it needs to support tracing right out of the box. And so RPC tracing is something we use heavily at Twitter today, and we've sort of modified the stock vanilla thrift protocol to accommodate for that, but it's kind of an ugly hack, and we want to make this a first-class citizen. So it's actually a pretty small project, but it's sort of non-trivial in terms of software construction. I'm going to show you, I hope, how elegant you can make these sorts of things. So first of all, I want to make sure that the kind of code that comprises finagle mux is maybe a little bit different from most Scala code. I care a lot about performance. I care a lot about memory allocation and so on. And that's because every single request that comes to Twitter will be dispatched hundreds of times over with this code. And even little bits of tuning will actually save us a fairly significant amount of money, it turns out. And so I'm going to probably pay a little bit more attention to performance and economy of allocation than you normally would. And do remember that you don't want to prematurely optimize. And I hope I haven't actually done that here, okay, and for our context at Twitter. So I just want to describe to you a little bit the protocol that we came up with. And then I'm going to dive into the implementation and sort of derive a set of best practices, I guess, from it. So first of all messages start with a size header. And so this is just 4 bytes, a big endian integer. And that describes the size of the rest of the message. Then there's 1 byte describing the type of the message, right? So we can have 256 different message types. And finally, there's a tag. It says 1 byte, but it's actually 3 bytes. That describes a client-assigned identifier that identifies a particular exchange. And so if I send a request, I assign it a tag, and when I get a reply, the server uses the same tag to answer that request. Does that make sense? It's pretty straightforward. So these messages, in turn, are split into what I call T messages and R messages. So T messages are ones that we transmit. R messages are ones that we receive. And the reason we make this distinction is that it makes clear who owns the tag namespace, effectively. And so if I send a T message, I'm responsible for assigning a free tag to that message. If I receive an R message, I'm responsible for matching that message to a T message that I previously sent, right? And so I need to maintain this map. And this is sort of a nice, concise way of describing this distinction. And so the kinds of messages that we'll see are things like trec and rec. That's to send a request and receive a response. I call rec just for symmetry. It really should probably be called response. There are control messages like draining, for example, and a bunch of other ones. But the protocol is extremely simple. So if I send a message of a given type, of a T type, I receive a reply of the corresponding R type, unless the server failed to process it, and then I'll receive a special message called R error. But there's nothing else. It's a very, very simple state machine for the messages themselves. So our first exercise is how do we model these messages? So clearly, if we want to implement this protocol, we need to have some representation of these messages that I've talked about. So what we decided to do is effectively extract everything that a message absolutely must have that's in common into a trait. Okay, and we seal it, and you'll see why later. What that is it's a message type, the tag that I described, and then buff is the rest of the message. Right? And so if I have a message, I know that I can always get a type, a tag, and the buffer describing the rest of the message. Inside of the object, message object, and actually there's a mistake here. It should be like this. Inside of the message object, I just created a nested object that actually holds the constant values for the message type. So these are the actual sort of protocol values. And this is also where I put all my case classes describing the messages. And so the nice thing about that is that this allows me to do things like message trec, and I know exactly what I'm talking about. I use the namespace to my advantage, and I can make the message types very short and concise. They correspond exactly with what we define in the protocol. And if I say message.trec, everybody knows what we're talking about. All the messages are defined in this file, which allows us to seal the message trait. And the nice thing about that is that now we can use the Scala pattern matcher to make sure that we have exhaustively handled all the messages when we actually implement it. This is a common trick. But it's a very, very important one because it allows us to use a type checker to make sure that we've implemented things correctly. And in fact, I used that heavily during implementing it. Right? I knew exactly what parts of the protocol I had or hadn't implemented, and the compiler would complain if I'd missed a spot. So that's the general pattern of how we model messages. So let's go into a little bit of the details. So let's look at an example message. trec. And so this is sort of the main message type. This is what transmits a request to a server. And again, as with all messages, it begins with a size. It has the type, the tag. And then we have 3 64-bit integers that describe its trace ID. So this is what allows us to trace messages throughout all of our distributed systems. Then it has a set of flags that describe some options, and then the actual body. Right? So it's pretty simple. And the way we model trec in this case is, again, just a case class. We say tag, trace ID, the request itself. Then we assign its type based on what I showed you before. And the nice thing about Scala, or about how we're using Scala here, is that when I say a case class and have tag and rec, for example, as part of that constructor, those are sufficient to satisfy the trait. So you'll see that trec extends message. But I didn't have to say val tag equals something explicitly. When I use a case class, it actually compiles down into the same thing, and that's enough to satisfy that trait. And so it's really nice and concise. And of course, the compiler tells me if I've failed to satisfy it. And another thing I'm doing here is that buff, which represents the rest of the message after the size, request, or request type, and tag, is lazy in this case. And that's because most of the time when I construct one of these things, I might not actually be interested in serializing. So if I'm receiving one of these messages, I'm not actually interested in serializing it again. And so I don't want to do a bunch of work if I don't actually need to do so. And the nice thing about using lazy vals is that it's really not that much more heavyweight than using having a method that manually populates some sort of shared field that you've declared. And in fact, the lazy can satisfy a method or just a regular val because they compile down to the same thing. There's methods in the end. And so this is very, very little overhead for a lot of concision. And it allows us to now compute this buffer lazily because half of the time we don't actually need it. Another sort of common thing in this protocol is that we have empty messages. So these are sort of pure control messages. For example, there's a message that tells clients to go away, not send any more requests. And there's a whole class of that. And so in order to sort of be able to concisely specify them, we create an abstract class called empty message. And it just specifies an empty buffer and takes the type in its constructor. And now I can declare these types of empty messages just like this. And again, this is enough to satisfy the message trait. And because empty message is abstract, it doesn't become part of the exhaustiveness checks of the pattern matcher, and the world is all good. And so these are the kinds of nice, just sort of syntactic shortcuts that you can use to very cleanly and simply model these kinds of messages. Another thing that is important in this implementation is that if I'm a server, for example, I might not actually understand all of the messages. But I might want to make a distinction between T messages and R messages. If I receive a T message that I don't understand, I want to return R error. If I receive an R message that I don't understand, then I've clearly done something wrong, right? And so another sort of common trick is to use these kinds of classifiers or extractors to make that distinction. So I can use these classifiers in my pattern matches along with everything else. And so in this particular case, we have an object called tMessage that has an unapply method that makes an extractor. And it returns a tag of a tMessage, or none if it isn't a tMessage. Right? And you'll actually see here, too, that we have a neat sort of trick. We reserve the most significant bit of the message byte to indicate whether or not it's a T or an R message. And so that allows servers, for example, to be forward compatible without knowing what exactly those T or R messages are. But it needs to handle them differently. And that allows me now to write code like this. I can say, well, if I have a message as a TREC, I do something. But if I have a message as a, after I've processed all the message types that I do know about, if it is a T message, then I might want to do, for example, return an R error. Right? And that's a very useful trick. Another kind of classifier that we use a lot, and in fact is coming also in Scala 2.10, is a classifier on exceptions called non-fatal. And that allows us to, for example, catch all non-fatal exceptions, but pass through fatal ones. And so again, these are sort of nice tricks that allow you to really use the power of the language and really make the way you model these messages compatible with how you sort of process them in Scala itself. And in this particular case, I can use the pattern matching mechanism to do all my work, right? Because I can have these arbitrary extractors. So now we have a model for our messages, a bunch of case classes that all inherit from the same trait. I can treat them in a uniform way. I can pattern match over them and so forth. Now, given a buffer that I've received from the network, I want to be able to decode it. And so I need some sort of, well, method in this case, from channel buffer to message. And that's actually very simple. We just read the header, extract the type and the tag, and then we match on that type and construct the message based on that type. And you'll notice that most of the messages here are actually really, really simple. They don't have a lot of data. There's really only two complicated messages. That's trec and rrec. And the key here is just to keep it simple. So I don't try to make this a first-class citizen of the world. Just have some utility methods that knows how to decode those two particular message types. There's no reason to introduce more abstraction or more infrastructure to generalize this case because it's such a small, there's just two types that require special treatment. And it's really great that we have such a powerful language, and you can use that power to avoid creating more abstraction. And that's something we do a lot, right? And so every time you think about introducing a new abstraction, think instead about how you might be able to use the language to be just as succinct, but without sort of introducing more structure if you don't really need to, right? And so we try to keep the minimum amount of structure that makes our code clear and succinct and easily understandable. And so I've just shown you how we decode messages. Now we also have to encode them. So this is the inverse operation, or bijective complement, I guess. So given a message, I want to produce a channel buffer. And again, you'll recall that the message type defined a buff, which was sort of the rest of the message after the header. And so all we have to do is encode a header and then concatenate it with that buffer. And you'll also notice that we made there's sort of an implied design choice here, which is encode and decode aren't methods on or rather encode in particular isn't the method on messages. And the reason I did that was basically that allowed the messages to sort of more or less be sort of pure values that I can pass around. And that's maybe mostly an aesthetic thing, but it does allow me to effectively guarantee that nobody overrides an encode, for example. And I know exactly what encode means. There's exactly one place in the code that defines it, and I can go and read it and understand it completely without worrying about inheritance hierarchies, for example. And personally, I find that style very appealing. It's very, very simple, and it sort of suits this notion of value-oriented programming. So now we've sort of gone over encoding messages and then decoding them. And that now allows us to essentially consume messages from the network and produce messages to the network. Now we have to do all the hard work. And so you can imagine that in a sort of a protocol multiplexer, you need some way of keeping track of idle tags. So tags that aren't yet taken. You need to be able to get a fresh tag and then give it back once you've received a reply to a message that used a tag in use. And so the basic gist is that we have to maintain a free set of tags, and in this case, the namespace is sort of 3 bytes, right? For this, we define a new trait. And so the idea is that we have a tag set, and you can iterate over it. So we have an iterable of int. That tag set is defined over some range. And notice here that we actually reuse a lot of the sort of Scala standard library types, right? And so range is just a Scala range. And the nice thing is that about doing that is that it really allows you to use all the methods that are already on range, code that already uses range, without needing, so basically when you have a concept that seems like it should already be defined, make sure you look for it to make sure that you reuse it. In order to acquire a tag, you call acquire. That returns an option of int. It's an option because you might have exhausted your tag space. And again, because it's a first-class idea, it's not an exceptional operation to run out of tags. We encode that in an option instead of throwing an exception, right? We really try to reserve exceptions for things that are exceptional, right? In this case, running out of tags is not. And then you can release it with release in this case. And another thing you'll notice here is that we sort of deal with primitives here. And so we return an option of integer, and then we can release the integer itself. An alternative design might have been to return some sort of wrap tag that has a release method on it that allows us to really control exactly what gets released. But in this case, that just creates more allocation for nothing, really. And so again, you'll recall at the beginning I said that we're really trying to pay attention to allocation in this code. So this is what a tag set is. We define a trait, and here's what we do. We hide the implementation, right? And so instead of just defining a class called tag set, say, or like a class called tag set implementation that actually inherits from the tag set, we hide it all together, and we make its construction just an apply method in the tag set object. And the reason for that is that now you're guaranteed that nobody can actually rely on the implementation details. Scala already gives you, to some extent, some ways of controlling that, like making things final and private and so on and so forth. But this really, really forces you to converse only in interfaces. And we found that to be really, really clean. It encourages us using composition over inheritance. In fact, it's impossible to use inheritance here. And most of the time is actually a better and simpler design than defining classes that you can construct. It also now allows you to change the implementation without having to change constructors, for example, right? So that's another common pattern that we use. We hide the implementation away completely, but the interfaces are exposed. Another thing that we need when we're implementing a protocol multiplexer is to have a map over these kinds of tags. And so you can, for example, imagine that if I am a client and I receive a request, I need to dispatch it. I need to keep some sort of handle on something that allows me to satisfy that request that's mapped from the tag itself, from the actual tag number. And that's what a tag map is. And so a tag map, again, is something that I can iterate over. And in this case, I iterate over tuples of ints and the type t over which we're mapping. I can map a new element in. And again, it returns an option of integers. So if that mapping succeeded, I get the tag back that it actually mapped onto. And then I can unmap it and remap it and so on and so forth. Pretty straightforward. We do the same trick again. And the way we construct the tag map is that we actually pass in a tag set. And so this now allows me to really separate out the behaviors. I've defined a tag set in one particular way, and then I'm just mapping over that tag set. And that also makes testing much simpler, because now I define the behavior of tag set orthogonally from that of the tag map. This is pretty sort of straightforward composition over inheritance stuff, but I think it really demonstrates the value of thinking in this way, right? In this case, as I mentioned at the beginning, we were really paying a lot of attention to allocations. And the way we're doing that is that usually you don't have that many concurrent requests, maybe a few hundred at a time. And so in this case, our tag map will try to make sure to put most of its mapping inside just a simple array, right? Because they're integers, I can just use an array index as a key, right? And the nice thing about the nice thing about doing that is that, well, one is we're using very, very simple and well understood data structures that don't imply any extra allocation. We're sort of optimizing for the common case. It's not normal to have more than a few hundred requests outstanding at a time. And we're very, very economical with objects in our hot path, right? And so really pay attention to those sorts of things. Keep everything very, very simple. Use arrays if you can, even if they're not as powerful as other things, and so on and so forth. Another thing that you'll see us doing here is we're sort of using composition over options. And so when I'm mapping an element, I acquire from the set, and then I just map over that result. And so that allows me now to essentially compose over failures. So if the acquisition fails, I don't have to special case that code. I'm just sort of mapping over the result of the underlying operation. And that's a very nice thing to do with things like options and futures and things like that. So finally, I'm going to sort of describe the actual client that does the dispatching. So given a request, I want to dispatch that request to the server, and then when the server replies, satisfy that request. And again, we're using composition, and the nice thing here is composition sort of tells the whole story of what's going on here. And so I have a client dispatcher. It takes some sort of transport. In this case, a transport just allows me to effectively write and read channel buffers. And what the client dispatcher is just a function from channel buffer to a future of a channel buffer, right? And so that sort of tells you what's going on. It tells me that I can give this client dispatcher a channel buffer. It returns to me a future of a new channel buffer. That the only sort of logical way or explanation for that is that channel buffer that's returned, or the future of the channel buffer that's returned, is to reply to my request, right? And so it's really nice to sort of, when you have well thought out types, oftentimes to sort of tell the whole story. And if you find yourself in a situation where you can't read a type and really sort of deduce what's going on, you should think about how you construct your program and try to figure out how you can construct your program so that that is the case. And I sort of use that as the litmus test for making sure that my abstractions are right. So this is basically what a client dispatcher looks like. I need to have a tag set, and then I have a tag map that maps those sets of tags onto promises. So every time I send a new request, I grab a new tag. I create a new promise, rather. I map it into the tag map. Then I send a TREC out with that tag. And now I define a function which I call every time I receive a new message. And I'm using this sort of weird syntax, but it's actually kind of nice when you get used to it. So I'm defining just a function. And that allows me to just use pattern matching outright without saying foo match whatever. And so what this is saying is I'm using type declarations to say val receive is a function from message to unit. And here's the function body. And that function body is just a pattern match. Pattern matches are technically partial functions. And I just match over all the message types that I know about and handle them accordingly. So if I receive a reply, in this case, that's OK, with a given tag and the actual reply, I try to unmap that tag. If I do so successfully, I set its value, and so on. So pretty straightforward stuff. But the nice thing is that sort of treating functions as first-class things is often very useful. For example, you're not going to see this in this presentation, but on the server side, the receive function is actually a var. And when I drain the server, I give it a different receiver just by redefining that function. And so functions are often very, very sort of useful little widgets that beyond just composition, because they're sort of first-class values, you can use them in a very flexible way. So another thing that we do is that, so I showed you the sort of receive function here. So that says, given a message, do something with it. That's what unit means. Now I have to actually receive it. And so I read from the transport. So if you remember, trans is the transport that I passed in initially. And I use recursion to effectively read infinitely. And so I say trans read, then flat map. I'll explain that in a second. So given a buffer that I got, try to decode it, receive it, and then loop again. If I get a bad message exception, then return a future exception, because then something's incoherent about the connection, and probably I need to shut it down. And this is actually the sort of receive loop. And the interesting thing about this is, first of all, the return value here is a future of unit. How many people here are familiar with futures? Okay, so like fair bit. So future is basically a promise for a value to be satisfied at some point in the future. And they compose like other Scala collections might. So you have map and flat map and for each and so on and so forth. And because they're so composable, they're actually very, very powerful. And so in this case, I'm saying loop is a method that returns a future unit. And I define it to be the following. I define it to be read a message from the transport, then take that message with its buffer, try to decode it, receive it, loop again. If I experience an exception here, then return a future exception. And you'll see actually that if you do the manual type check here, it works out, right? Because loop is, again, a future unit. And so everything's consistent. And so what will happen basically is, as long as everything is successful, I'll keep on reading. But the moment I fail, this outer future will fail as well. And that allows me now to write code like this. I can say loop on failure, then the exception. I can close the transport, and then all the outstanding requests I can fail. Right? This allows me now to isolate my error handling away from everything else and treat them sort of orthogonally. I've modeled my loop as sort of a failable entity, right? And I represent the ability of that entity to fail by returning a future unit. And then I handle that separately. I just start the loop, and if the loop fails, then do this. Close the transport, fail all the outstanding requests. Right? And it's very, very nice to be able to treat your errors in a separate way, in a distinguished way, instead of sort of interleaving all your error handling together with your sort of dispatch code. And that makes it much easier to reason about. and also very, very concise. And the keen reader might actually notice how the hell this actually works, because you'll notice that when I flat map, I could potentially be creating an infinite chain of futures, right? And so the outer future is, the first future flat map with the second future, flat map with the third future, and so on until all the messages are read. It turns out that our future implementation actually knows how to compress flat maps down to 1. And so we don't actually create these intermediate futures. And this is the exact dual of tail call elimination for futures, or for flat map. Yep.
Time out of that.
So the question was, how do you time out of that? Great question. So in this case, we don't want to time out. This is a client that just keeps reading, right? If the transport closes, the read fails, okay? If the connection fails for whatever other reason, the read fails, right? And so if I want to close it, I just close the transport, and the read will fail, and I'll do the right thing. But I don't want to time out, right? I want to wait infinitely long for messages, because it's a true multiplexing transport, right? And so I'm just receiving control messages, and I don't care if they take a long time. So, yes. And again, we're sort of using composition very, very heavily. We're separating our sort of error domain from our application, our value domain. And that's very, very powerful. So another thing that I've started doing a lot is, and sometimes it's often to sort of clarify your own thinking and approach to the problem, is I've started very much writing package documentation. And what I usually put in the package documentation is a little essay about what this thing is and what it does. And it really helps me clarify my thinking and how it fits into everything. It turns out that writing is just like writing code, actually. Writing English is often a great tool to gain clarity. And so I usually do this sort of thing. I make a package doc, and I write about what this package does, and try to explain it sort of holistically how it fits in, with the rest of the program or library or whatever. And I personally found this to be a very, very useful tool, and obviously users do as well, because now I'm sort of exposing what I'm thinking, which is good. Another thing I've been doing a lot is I've really been looking at my Scala Doc output. And so when I'm writing new packages like this, I generate my Scala Doc and I ask the question, everything you see here, first of all, does it make sense for an end user to see this? Right? Do all these things make sense? Am I leaking implementation details here? Would a new user sort of grok what this package is doing based on the names that you're seeing? Can they click on it and understand what's going on? I guess you could call it sort of Scala Doc-driven development. But basically, I've started really hiding everything that doesn't belong in the Scala Doc. If you can't justify something being an external interface, hide it in the package. It turns out it's much, much easier to make something public than to make it private later. The latter breaks APIs, and the former doesn't. And that's something that's bitten us a lot before. We've created things that were meant to be in implementation detail, and people started relying on it, whether you like it or not, and now we're stuck, right? And so we've been very, very careful to sort of curate what our public namespace looks like, and that's been very, very helpful. And again, you want to sort of ask yourself the question, given the Scala Doc, can you sort of deduce, can you infer what's going on here, what this package is about, and if you can't, make sure that either you restructure something or you document things, and so on and so forth. And I've found that this helps not just users, but the developers, right? Like it really helps clarify your thinking, how you're developing, how you're structuring these packages, and it's a very, very useful just sort of thinking tool. So that's all I have to say about finagle mux. Watch, I guess GitHub next week or something, we'll probably push it. And again, I mentioned in the beginning, I'd written this guide called Effective Scala. I think it's actually the first hit on Google if you search for Effective Scala, but if you'd like URLs, here you go. We also have something called Scala School, which is now actively maintained. We actually have a tech writer who's maintaining this. It's awesome. And so we're really trying to help the whole Scala community, not just internally. We think that we can make basically all of our internal education materials available outside as well. And that's all I have to say. Are there any questions?
On the example of blue, why couldn't that in a future, why
So the question was, in loop, why couldn't this be a type other than unit, or could it perhaps even be an either or something? So you could make it something other than unit, but what would you make it? You don't really have anything to return other than the fact that you either succeeded or failed, right? And so in other words, there's nothing really to communicate about it other than the failure itself. In terms of either, no, because trans.read returns a future of a channel buffer, and you want to compose over that. Yep. So the question was, could you have made it a future of nothing? Yes, you could. Mm-hmm. And the nice thing, actually, that's a great point. I'm going to go change it. So the question was, could you make it a future of nothing? Yes, you could. The nice thing about that, and this is my next tip, is that that actually allows you, or this allows users from matching on the return type itself, right? And so you can now guarantee in the type system that users of this interface can only know about errors and not successes, right? Which is often kind of nice. Yep.
So here, regarding a best practice with no argument method names,
yep.
Are you using the parentheses on this to essentially indicate that there's a side effect?
Yeah. So the question was, with respect to no argument method names, how are we using parentheses? Yes, the supposition, that's correct. We're using parentheses here because we're using side effecting operations, basically. So by convention, whenever there's side effecting operation, we tend to use parentheses. Yep.
So this is a finagle future, right?
Yep.
So the tail call optimization, this is the feature of implementation of finagle futures.
Yeah. Yeah, so the question was, this tail call optimization, is it a feature of finagle futures or Twitter util futures technically? Yes, they don't yet exist in Scala. I'm working with Philip to make that not be the case. Yes. All right.
Look for Micronautics research for pragmatic Scala training, architectural design, implementation, and systems integration. Ask about our complimentary introductory presentations on Scala today.